Okay, Faisal. Let's look at this example. Distributed forces. Let's look at beam. This is an example of a beam that might come in statics. See this beam in top of a beam. So there, you can see them. This is the way they put the beams connected with each other. In a house, this is like a steel house, like in Walmart and Kroger, the way they design a steel house. Generally, if there is a beam like this, see, look at this beam. This beam has a hinge and has a ruler, and you can see that there is a concrete slab. There is like a ceiling in top of it. Look at the ceiling. And the ceiling has a load, and this load is distributed load. So you can see that there is a uniform load. It has the same weight, the same thickness. So this is one example of a load. And you can see sometimes it's a uniform load distribution. It's uniform. Sometimes the load is triangle. And sometimes the load is as a function like that. Okay? So we will give an example. Let's look at an example. And see if you have a load like this. There is a hinge, 1 meter, 2 meter, 1 meter. And a ruler, and this distributed load is 3 kilonewton per meter. And look at this. It's going from here to here. It's only 2 meters. Well, first of all, the questions need find the reaction at force A and at B. And this is the loading, 3 kilonewton per meter. And look at this. 1 meter from here to there, 1 meter from there to there, and 2 meters from here to there. So, first of all, we remember that here there is a hinge, there is AX, and there is AY, and there is BY. And this distributed load, remember it was what? It was 3 kilonewton per meter. So it is 2 meter. This is the distance from here to here. So 3 kilonewton per meter times 2 meter, that is 6 kilonewton. And it is in the middle. This is 2 meter, so it's going to be the load in 1 meter from here and 1 meter from there. 6 kilonewton, you can see it's 6 kilonewton, and it is in the center because it's a triangle. So it's in the center between 1 meter from here and 1 meter from there. So now we could find summation. Of course, AX is 0 because there is no other reaction in the x-axis. So AX is equal to 0. So summation of force at x gonna make AX is equal to 0 because this is in Y, this is in Y, and this is also in Y. So let's take summation of moment at A. This is BY gonna go counterclockwise. BY times 1, 2, and 1. So this is 4 meter. So BY times 4. And then this one, it's 6. And this is gonna go negative because it's going to go clockwise. This is 1 meter from here and 1 meter from there. So 6 times 2, negative. Minus 6 times 2, negative. So this is the equation for summation moment at A equal to 0. You'll end up with BY is equal to 3 kilonewton. And now, summation force at the Y equal to 0, you could find, if you know BY, you could do summation force at the Y equal to 0, AY minus 6, plus BY equal to 0, and then you do it like this, and you'll end up with AY is equal to 3 kilonewton, and that is one of the examples. Okay. Let's look at another example. This is a very weird shape, and you could see this in some Walmarts, that this is the loading in top. Find the reaction of A and B. Look at this. Of course, if he gives you a distributed a load like this, he should give you the loading equation: 2x squared plus 8x minus 2x squared. Okay. So first of all, we have to draw a 3-body diagram. Remember, a hinge, a ruler. Okay. So let's draw a 3-body diagram. We have to do the integration. Now, remember, it is, let's take it from here. 0 to the whole loading. The loading starts from this point, you could call it 0 to 2 and 2, 4. So the integration from 0 to 4 for the loading dx. This is the way to find the area under that loading. So 0 to 4, and you should put the equation minus 2x squared plus 8x. So remember, minus 2x squared plus 8x. So you find the integration, and then once you find the integration, the answer would be the equivalent force 21.33 kilonewton. Now, so you have the equivalent force 21.33 kilonewton, and this is AX, AY, and BY. And that's going to be in the center of that because there's a uniform. So this is like the image at this point, so it's going to be in the center of this beam. Okay, the best is to find moment at point A. We'll do the same thing, moment at A. By gonna give you positive, By times 4. And this is minus 21.33 times 2. Okay, and then By is equal to 10.67 kilonewton. Now you do summation of force at the y equal to 0. So Ay minus 21.33 plus 10.67. This would give you Ay is equal to 10.67. And that is second example. That's a very easy example. Let's look at the third example. This is one of the examples that you need to analyze, of course, later on for the shear moment diagram. Let's look at this. This is, if you see it like this attached to the wall, here there is reaction in the x, AX, AY, AX, and moment at A. So AY, AX, and moment at A. So this is attachment to the wall, 1.5, and then you can see the loading up to kilonewton per meter, and it is uniformly going up to 4 kilonewton per meter. So this is a weird looking load. So we have to look at this loading, find the reaction forces at the fixed support A. So there is no other support, only fixed A. So here, as you said, there is a reaction in the Y, there is a reaction in the X, and there is a moment at A. So we should do a free body diagram first. This shape, that is a weird shape, it might be containing a triangle and a rectangular. So this is the triangle, goes from 2 kilonewton per meter and goes to 4. So which means that if you make it like this, that is 2 kilonewton here, and the distance from here, you can see it here, it's 1.5 meter. So this distance is 1.5 meter. So let's take the triangle. So the triangle 0 to 2, remember? It's 2 if you take it all the way here. So this one is 4 minus 2, so it's 2 kilonewton per meter, and this is 1.5. Plus the other triangle, which is going to be, look at this, this is 2. This is 2. 2, that's 2. And this is 1.5. So you have a triangle and you have a rectangular. For the force equivalent for the triangle, it's 1/2. This is 1.5, 1/2, 1.5 times 2. 1/2 the base times the height. That is the equivalent force of this rectangular, which is 1.5 kilonewton. For the rectangular, it's not 1/2 base times height. It is 2 times 1.5. That's 3 kilonewton. So this is, we find the resultant for the rectangular, and we find the resultant for the triangle. So now we're going to put the free body diagram. There is a reaction AY, there is a reaction AX, and there is a moment at A. Now, there is 2 equivalent forces, one for the triangle and one for the rectangular. Remember, the rectangular, it's at the center. This is 1.5, so it's going to be 0.75. So we should do it. This is the 3 kilonewton for the rectangular. This is 0.75 plus 1.5, because if you look at it here, this is 1.5 and this was half of it, so 0.75 plus 1.5, this is the location of the rectangular, 3 kilonewton. 0.75 plus 1.5. For the triangle, it's 1.5 kilonewton and it is 1/3 the base and 2/3 the other side. So 2/3 the other side, which is what's 2/3? This is 1.5. Remember, it's 2/3, so it is 1.5, 1.5, 1.5. That is 1 because 0.5, 0.5, 0.5. So if you do 2/3, it's either, as you said, it is 1/3 from here, which is 0.5, and 2/3 from here. So it is 1. So 1 plus 1.5 is 2.5. And that is the location of the rectangle, triangle. So right now we have this location. Now we could find out the equation for this. Let's first of all do moment at A. If you do summation of moment at A, we could find out moment A. So summation of moment at A, this reaction is gone and this reaction is gone. Of course, AX is equal to 0 because there is no other reaction in this that is in the x-axis but AX. So summation force at x equal to 0, AX will be 0. Now we have this reaction, AY, and we have this moment. So the best is to find moment at A. So moment at A will give you the moment at A here. So moment at A, and this is gonna be positive. Okay, moment at A. Remember, this is gonna go negative 3 times 2.25 negative 3 times 2.25, and this is gonna go also negative 1.5 times 2.5 negative equal to 0. So this is the moment. So you'll get the moment 10.5 kilonewton meter. The moment units, be careful, it is kilonewton meter. It's not like the reaction. So we found the moment 10.5 kilonewton meter. Now let's do summation of force at y equal to 0. We have 3, we have 1.5 going down, and we have this. So it's going to be 4.5 up. So summation of force at y equal to 0, this is 4.5 kilonewton up. Okay, and that's AY. That's it. Very simple. Very simple. We made this look like a rectangular and a triangle. Hopefully this will help.